first speaker is Bernard Leclerc. He's either going to speak about algebras, representation as well, subalgebras, quantum group algebras, or possibly just quantum algebras, cluster algebras, and quantum group algebras, something like that.
Yes. Okay. Can you hear me? Yes. This is. How does it look? So can you hear me? Yes. Yes. I made the title a little shorter, but this is the same content as what was announced in the abstract. So this is a joint work with David Hernandez, and in fact we started collaborating on this topic in 2008, and it turns out that in ICRA 2010 in Tokyo, I had already the opportunity to give a mini course on the beginning of the story. So I wrote also my lectures in these proceedings. So if you want to have an introduction to the presentation theory of quantum group algebras and how they connect to cluster algebras, I think you could refer to this proceedings. So today I want to tell you about some more recent progress. I think it would not be a good idea to just repeat what I told in 2010. So please look at this for an introduction to the quantum group algebras and why representation theory is interesting from the point of view of math physics, for example. I'm not going to say this today. So let's see if I can use this machine. Okay. So I need some notation and background to get started. So we start from the usual datum of a Cartan matrix. Here I mean a really of linking type, so from classification from AN to G2. And this Cartan matrix is always irreducible, meaning that you always can find a diagonal matrix with integral positive entries, such that D times the Cartan matrix is symmetric. And I will normalize this B so that the smallest entry is always 1. And this makes it unique. Right? So we will see these entries DI occurring many times. Okay. So from the Cartan matrix C, you can define a certain complex Lie algebra, simple complex Lie algebra. This is a Cartan filling classification. So this is finite dimensional Lie algebra with a complex number. And now you can also define an infinite dimensional complex Lie algebra by tensoring with the Laurent polynomial in one variable, and this is called the loop algebra. So the Lie bracket is the obvious one, where you use the Lie bracket of G to define the Lie bracket of this L of G. Now, the algebras which I want to discuss today are the quantum deformation of those, namely the so-called quantum group algebra. So you take the enveloping algebra of the group algebra, and then there is this theory which was developed by Greenfeld and Jimbo in the 80s, which associates to this algebra a certain Q deformation. And for me, the deformation parameter will be always a complex number which is not the root of 1. So, we are interested in the finite dimensional representation of this algebra. They form a nice category, which I will denote by script C. And this script C is in particular a tensor category because UQLG is above algebra. So we have a tensor product of representations available. So there are many things which are known on this category. For example, the classification of simple modules. And many other things, but there are also lots of open problems. And for example, again, if I want to stick to the description of the simple modules, in contrast with the representation theory of G, where we have this classical Weil character formula, here for UQLG, the simple modules, we don't have any analog of this biochemical formula. So it is still an interesting question to find, let's say, nice description of the irreducible module. Okay, so now the prototype of the results which we have with David and which were also developed by other people after we started. So I put the name of Nakajima, Kimura and Francine also gave a very nice lecture Wednesday afternoon on his recent result in this direction. So this is rather a meta-theorem which says that the connection with cluster algebra comes in the following way. We have been able to describe certain, and here I'm being rather vague, I will be more precise maybe later, certain monoidal subcategories of this tensor category such that the corresponding rotating ring can be equipped with a nice cluster algebra structure. And this is the way we want to use cluster algebras as a combinatorial machinery to understand better the simple objects or the characters of the simple objects in this category C. So I will try to be more precise. First, let me define for you a cluster algebra. So again, we start from our cluster matrix, and everybody knows, I suppose, that the cluster algebra, at least a skew-symmetric cluster algebra, is given by a quiver. So the quiver here will be the following. So I denote by capital I the set of vertices of the Dynkin diagram, or if you prefer, the parametrizing set of the row and columns of the Carter matrix. And I take an infinite vertex set where I take second component, which will be an arbitrary integer Z. And now that the arrows of the quiver will be given by the following very simple rule. There will be an arrow from R to JS if and only if the entry in the Carter matrix Cij is non-zero, and if you look at the second component, S must be equal to R plus Dicij. So Dicij is an entry in row I and column J in this symmetric DC, this symmetric Carter matrix. I mean, it's the product of the Carter matrix by the matrix D. Okay, so if we want to define a cluster algebra, we need to introduce a set of variables, one for each vertex. Let me call them Z. And then, okay, yes. And then we can define A, the cluster algebra, with initial C given by this quiver and this set of variables. Fine. So let me give you a feeling about what this quiver looks like. So this is type A2. You have the Carter matrix, which is written up there. Here it is symmetric, so you don't have to multiply by 3. And so, for example, we have the diagonal entries which are equal to 2, and this will account for the vertical arrows in my quiver, right? And the off-diagonal entries which are equal to -1 will account for the descending arrows, right? For example, from 1, 2 to 2, 1, yes, I have an arrow because the corresponding entry is -1, so it's not 0, and I have to decrease the second entry by -1. I mean, to add -1. Right, so I guess everybody can recognize this quiver. This is the Ausländerheiten quiver of the derived category of a quiver of type A2. Except that I want to include the arrows corresponding to the Ausländerheiten translation here. They are part of the quiver. These are the vertical arrows. Usually we draw this quiver maybe horizontally. But so this would be similar description for every ADE type. But for the other types, B, C, and G, we have to take into account the matrix which I call D. And here is, for example, what you get in type B2. So here you see, after symmetrizing, the matrix B times C will have the 4 minus 2 on the first row instead of 2 minus 1. So it will be 4 minus 2 minus 2, 2. And this means that the vertical arrows on the columns where the first component is 1 will jump with the second parameter will jump by 4. Whilst on the column with first parameter 2, the vertical arrows, the second coordinate, will jump only by 2, like this. So I don't know if anybody has seen such a quiver attached to the datum of type B2. I would be pleased to know if this reminds you something. It's not a nice Außenhaltung quiver as far as I can see. Maybe also, I think I should say, I said before that I would take for the second component any integer, and here you see in this picture I have only even integers. So in fact, if I would really use the definition which I had before, there would be a second connected component where you shift all the second part of the vertices by 1. So this is what happens in general, and I don't want to mention these two identical copies. We can work with the cluster algebra corresponding to just one of the copies. It's not the cross by data. Okay. Any questions so far? So that's our starting point. So this defines the cluster algebra. Now, what is the relation between this cluster algebra and the representation theory? So this category of finite dimensional objects C. I can make this work. Yes. So, if we start from a simple object in this category C, so this is a finite dimensional representation, and the general theory of this quantum group algebra tells us that we can associate to it a certain Lorentz polynomial, which is called the Q character of this representation, and which characterizes the representation if it is simple. It characterizes it up to isomorphism. So if you know the Q character of a simple object, then you know what is a simple object. And the variables in these Q characters are usually denoted by this letter capital Y. So you should pay attention to the indices. The first index is, again, the vertex of the linking diagram. So in this capital I, and the second index is an arbitrary non-zero complex number. Fine. So this is from the point of view, from the side of the quantum group algebra. Now, from the side of the cluster algebra, we can start from a cluster variable, or more generally a cluster monomial, and by the Laurent phenomenon, we know that every cluster variable or cluster monomial is a Laurent polynomial in the indeterminates of the initial seed. So here this ZIR. And so now the main observation that we made at an early stage, actually, when we were working on this with David, is that there is a way to relate these two types of Laurent polynomials, namely, if you make this simple-minded change of variable, so you, you can read it. Here, everything is explicit in this formula. So, yes. So maybe I should say that in this formula, from the side of the variable y, the complex number, which is denoted by a up there, is always the power of q. But this is not a restriction. So we for general reasons which I don't want to go into, it's enough to consider Laurent polynomials for which q characters for which all these a's are going to be powers of q. So we can certainly do that, and then we can decide to do this little formula, and this formula looks a little bit mysterious, but it turns out that if you do this change of variables, then we discover that many simple objects in this category, their Q character is equal to some cluster of monomials in this algebra. Let me make it a little concrete by giving you one of the simplest examples. So let's start with, so this is type A2. Type A2 means SL3. So I didn't say anything about this quantum group algebra, but I suppose everybody knows that SL3 as a Lie algebra acts on the three-dimensional vector space. This is the defining representation. And it turns out that there is one parameter family of corresponding simple representations for the corresponding quantum group algebra. For the Lie algebra, this defining representation is associated with the first fundamental weight, pi 1. And in this case, the corresponding family of modules for the quantum group algebra, they will be labeled by the highest weight, which will be encoded in this variable y1, q. So if you have never seen a q character before, maybe the only thing that you could see from this formula is that we have three monomials. So this means that the dimension of the corresponding representations is indeed 3. So this represents the character of a certain three-dimensional irreducible module for the quantum group algebra of type A2. Okay, and now we have this cluster algebra of type A2, which I mean related with A2, which I showed you before, and you can do the following. We have a vertex numbered 1, 2, so you could first start by doing a mutation there, and then you follow by a second mutation at vertex 2, 3. So I don't want to do the calculations, everybody can do that. And I claim that then the new variable which will appear at vertex number 2, 3 will be what I have calculated here. So we know that it has to be a Laurent polynomial in the variable z, and this is explicitly which Laurent polynomial you get. And now you see that if you compare the two formulas and you use the change of variables which I showed in the previous slide, then you really have that they coincide. And so this is not an isolated phenomenon, and we were able to prove with David that this holds generally for all Kirillov-Reshetiki modules. So Kirillov-Reshetiki modules, if you have never heard of them, this is an infinite class of simple modules for these quantum group algebras, and they have been studied intensively, first because they arise naturally in the problems related with mathematical physics, and also because in some sense they are the most accessible simple modules. So those for which we have some way of calculating, or at least of writing some relations between the Q characters. So we proved that, and in fact we don't think that this observation is restricted just to the Kirillov-Reshetiki module, and there is a main conjecture here. We say that a simple object in this category C is real if the tensor square is simple. And our conjecture is that the Q characters of all the real simple objects in this category should be equal to some cluster monomials of the cluster algebra A that we had before. Again, under the same change of variables. And okay, if I want to say just the cluster algebra that I had before, I should say that up to shift of this second parameter. Because here I'm always assuming that we have again integral power to Q. But this is something, this is not a relation code. So, this is a conjecture, and I mentioned before the lecture of Fancy, and in fact this lecture, I don't know if some of you at least attended this lecture, and this result gives very strong evidence for this conjecture in type ADE. The problem why it is not exactly proving the whole conjecture in type ADP is that there is always this question that was mentioned several times of reachability. So is it possible to reach every cluster from the initial seed by a sequence of mutation? So here, this translates into the following question. So from King's results, well, we know that many real simple objects will have this property, but in order to be sure that these are all the real simple objects, we need to know that all the real simple objects are connected by some mutations, and this is not here. Okay, but another thing which is missing in the work of Tim is that this is only for type ADE, because he's using in a crucial way the Nakajima geometric approach to the representation theory of QLG, and this is not available for the remaining types. And in contrast, our theorem above works perfectly fine for all types. Okay, but there is still something which is also strange in this conjecture, which I have highlighted in blue here. So I'm not claiming that the Q character of all the real simple objects are equal to all the cluster monomials. This is certainly not true. And you see, if I go back, let me see if I can go back. Yes. So here we were able to identify this cluster variable to this Q character, because it turned out that this cluster variable was, in terms of the variable z, it was expressible in terms of quotients of two variable z. But what about the initial variables? So the initial variables, for example, z, I, j, there is no way you can express them in terms of the y's. So they cannot give you something which is the Q character of the simple object. And if I had done only one mutation here, we would have a similar problem. We would obtain some Laurent polynomial, but it would not be of homogeneous degree 0. So there would be no chance that this is the Q character of the simple object in this category C. So, yes. So this is the contents of this comment here. Some cluster variables of A cannot be Q character of simple objects in C. And for example, the initial cluster particles, and in many cases a one-step mutation of the initial cluster variables are certainly not the Q character of some object in C. So what is their meaning then? They should be related somewhere, in some way to this quantum group algebra. And the natural idea that comes to mind is maybe this category C is not big enough. Perhaps there is another category in which we could embed the Grothendieck ring of C, so that then there would be also an interpretation for the remaining cluster variables. And it turns out that this new category O, well, it was called O by Hernandez and Jimbo. It was introduced completely independently of our work by David and Jimbo in 2012, and studied further with Ed Frankel in 2015, 2016. And the main message of my talk today will be that the remaining cluster variables and cluster monomials should be some classes of simple objects, but now in this larger category O. So this is what I want to explain today. So let's see if I can make it. Just some very general things about this category O. So the way it is defined, it's no longer a category of representation of the quantum group algebra, but only of what they call the Borel subalgebra. So the quantum version of a Borel subalgebra of this group algebra. And also the other interesting feature is that the corresponding objects in this category are infinite dimensional in general. But it turns out that it also contains some finite dimensional objects, and that these finite dimensional objects are very closely related to the objects of the category C. So we can indeed, in fact, embed the Grothendieck rings, as I said before. So what I would like to do in the next 10 minutes or so is to give you a very rapid introduction to this category O by showing you how it works in the simplest case, namely SL2. Oh, I forgot one thing. Yes, the building blocks of this category, which were constructed by Hernandez and Jimbo, they are called pre-fundamental modules. So these are some particular simple objects in this category O that they construct first. And they are denoted L plus, L minus, and they are indexed by the same kind of datum. So the vertex of the linking diagram and the non-zero complex number. So what I want to do now is to show you how you can construct these pre-fundamental modules in the case of SL2. Pre-fundamental modules in type 1. So let's start from the very well-known UQSL2. So this is not loop yet. So everybody has seen, I suppose, this algebra before. It is generated by three element EFK, where K is invertible, and you have this familiar Q deformation of the circulations. Fine. And now, before defining UQLSL2, let me define UQSL2 hat. So SL2 hat is a finely algebra associated with SL2. So it is in this Greenfeld-Jimbo construction. It comes from the Carter matrix of affine type A1. So this is this 2 minus 2 minus 2 Carter matrix. And using this Carter matrix and the list of generators, now we have E0, E1, F0, F1, K0, K1, and similar relations encoded in this Carter matrix, which I'm not going to give you. They define for you the UQ-SL2 hat. Okay, and now UQ-LSL2, so the loop algebra, is the quotient of UQ-SL2 hat by the relation K0, K1 is equal to 1. Yeah, so it turns out that you could study a finite dimensional representation of UQ-SL2 hat, but they would all factor through this quantum loop algebra. So it's enough to work with the quantum loop algebra. Okay, so how can we construct representation of the quantum loop algebra? It's rather easy because we have so-called evaluation homomorphism. So these are algebra homomorphism from the quantum loop algebra to the simple-minded UQSL2 up there, which are given by this very explicit formula. So you see we identify E1, F1, K1 with UQSL2 by mapping them to the corresponding EFK. And then for the second SL2 triplet, E0, F0, K0, then we sort of switch. E0 goes to F, F0 goes to E. And we can even introduce some free parameter A in the formula, and it's easy to see that this gives you an algebra homomorphism. So this is clearly subjective. So now if you start from your favorite representation of UQSL2, you can pull it back to UQLSL2 with all this evaluation homomorphism, and then you will get a one parameter family of representations of UQLSL2. So let's do that. So we start with the UQSL2 module, irreducible module of dimension n plus 1. There is only one, and the explicit formula are well known. The E generator acts as a raising operator, the F acts as a lowering operator, and here in my formula the bracket means Q integers. Right? So I plus 1 is Q to the I plus 1 minus Q to the minus 1, I minus 1 divided by Q inverse. And all these vectors VI are weight vectors, namely even vectors for K. So if we now lift this with the evaluation at A, we get a representation of UQLSL2, where the formula will be like this. So I only wrote for you E1 and E0. E1 will not contain this parameter A, but E0 will contain this parameter A, and Okay, I don't need to write K0 because K0 is just an inverse of K1 since we are in the loop algebra. But you could write also F0, F1. Now, the idea behind these pre-fundamental modules is that we want to let the dimension n tend to infinity here. So we would like to take sort of limit of this family of irreducible representation where n tends to infinity. But we want it to be a representation, so we want that the formula giving the action converge in some sense. So what we can do is the following. We can take for A q to the n minus 1, and we can assume for a moment that q is of modulus strictly bigger than 1. And then, I mean, it's an easy verification that you can do at home. You can let n tend to infinity, and these first two formulas will have a limit. Namely, well, for the first one, q and a do not appear, so there's nothing to prove. But in the second one, you can do the calculation using the definition of the quantum numbers, and you will get this formula here. Now, of course, the last formula does not make sense because q is bigger than 1, so if n tends to infinity, this will go to infinity. And then you will normalize it. Somehow you make you just remove this n, which is creating the problem, and you can still check that this guy satisfies the correct relation. Let's say the correct relation not for the UQSL2 hat or UQLSL2, but at least for the subalgebra generated by E1, E0, and K1. And this algebra is precisely what they call UQ of B, the Borel subalgebra. So this means that in this way we have found an infinite dimensional module for this Borel subalgebra generated by E0, E1, and K1. So we should not be worried by the fact that we have assumed that Q is bigger than 1, because this was just a device for guessing the formula. Once you have the correct formula, you can check that they work, that they satisfy the relation for any Q. On the other hand, you can also check that that this representation cannot be extended to UQLG. So there is no way you can also simultaneously include the F0 and F1 acting on this module. So it is really a UQP module. So this is the first pre-fundamental module for UQLSL2. They denoted by L minus. It turns out that you can also do a similar thing with a different choice of parameter. Namely, let me just only change what is going to be changed. So look at A. Now it was q to the n minus 1. Now it becomes q to the minus n minus 1. And I also assume for the for finding the formula that q is now less than 1. And then you get a very similar formula, but with these new signs here which were not before. And this is the positive pre-fundamental representation L plus. Okay, and so we are almost done for SL2, but I want to stress that in spite of the similarity of the definition, these L plus and L minus are quite different. They have very different structure, and in order to see that, one should consider how a certain commutative subalgebra of UQB acts on this representation L plus and L minus. So it turns out that UQB has a very large commutative subalgebra with generators denoted by phi k, where k is any positive integer. I don't want to go into defining precisely what are these phi k, but the first phi 0 would be just k1, and then phi 1 would be this bracket, and then it gets more and more complicated, but there are some nice generating series which allow to define this commutative subalgebra. And the point is now, if you have a commutative subalgebra inside your algebra, then you can do some you can do some order decomposition of the representation. So you can look at the joint eigenvalues of all these phi k. So, what is going now? Yes. So the way physicists do this, they take a generating series of all these phi k. So they introduce a new formal parameter uk, and they want to see how this generating series acts on the vector of the representation. So here are the formula that you can calculate. It's not a trivial calculation even for SL2, but you have to believe me. So every weight vector vi in this infinite dimensional representation, either in L plus or in L minus, is an eigenvector for this phi u. And here are the corresponding eigenvalues. And so the two formulas are quite different because the first one, you only have a polynomial, which means that phi 2, phi 3, etc. Will act by 0 on vi. Whereas in the second formula, you have a rational function, so you should interpret this as taking the power series expansion, and then you see that all the phi k act with some non-zero coefficient on this representation L minus. So anyway, we have these two different representations, and because of this, so if you look at the eigenvalue on the highest weight vector, namely v0, with L plus you obtain this 1 minus u, and with L minus you obtain this 1 over 1 minus u. And we call this, or they call this, the highest loop weight of these representations. So we have two different highest loop weight, one which is a polynomial and one which is a rational function. Okay, and finally, I have to recall that there is this shift automorphism which I mentioned a little bit before. So for UQB, it is this algebra homomorphism defined by the formulas which I have put here. So again, A is any complex number, any non-zero complex number, and by using this shift automorphism, you can twist any irreducible representation, and you will get a new irreducible representation. So if you do that with this pre-fundamental representation, you get what I call L plus A or L minus A with the corresponding highest loop weight. Now we have all the pre-fundamental modules in type A1, at least the non-trivial one, because you still have, yes, you still have also the, a bunch of now kind of one-dimensional modules for this UQ of B. So for UQ of LG, you don't have, except for the trivial module, you don't have one-dimensional representation. But for the Borel subalgebra, you have many one-dimensional representation, and they can be parameterized by the weights of SL2. So this is my notation. It will be lambda between brackets. And we call this a zero pre-fundamental module. So, as I said before, these two fundamental are the building blocks of this category O. So I won't give you the precise definition of the category O, but because I just want to see the Grothendieck ring, so I only need to know what are the simple objects. And the simple objects are all the composition factors of tensor products of arbitrary number of pre-fundamental modules, positive, negative, or zero. So simple objects of category O. Yes, subquotients of tensor products of the fundamental modules. So now you know more or less how to do that in type A1. In their paper they do something for any type, but they cannot work naively like I did now using explicit formula. So they have really to work to show that there exists a family of what they call pre-fundamental modules. So I'm not going to go into that. Yes. I wanted to, add that from the construction, all the simple objects in this category O will have a highest loop weight, and this highest loop weight will be in general a rational function. And in fact, any rational function is allowed with the only condition that it should be non-zero when you specialize to zero. So this gives a parameterization of all the simple objects. Now in arbitrary type, it's exactly the same, only that now we have more generators for our quantum loop algebra. So the quantum Borel subalgebra is generated by the E's and the K's. You omit. And there is also commutative subalgebra now, but which has even more generators. Okay, and you can define the notion of highest loop weight module. This is a module which has a generating vector for UQP, which is filled by all the EI's except E0, and which is an eigenvector for all the phi i's. And okay, what else? Yes, and so again, I want to make it short now. In a similar way, they define pre-fundamental positive and negative module, but now we have one for each vertex. We have family, or rather two families for each vertex of the Deakin diagram. So you will have this additional index I, and again, the simple objects in the category O are highest L weight modules with now the highest weight will be not just one rational function, but an R table of rational function. Okay. Oops. Now what? Yes. This is the same as before. The simple objects are the subquotients of tensor products. Yes. Now, what about the finite dimensional modules? I said that they were also inside there. So it turns out that if you take the following, so you see I have this notation psi plus IA and plus psi minus IA. These are the highest weights for these two types of pre-fundamental modules. Now I can multiply them. In fact, I have things labeled by arbitrary rational functions. So I can do, in particular, I can consider the following highest loop weight. And let's denote it by YIA, like we had before. And the reason is because if you calculate this representation now of UQB, then you can show that it is finite dimensional, and that in fact it is a restriction to UQB of a fundamental UQLG module. So we recover all the fundamental UQLG module inside our category O, and you can even show that every simple finite dimensional module in O is of the form, okay, you take a simple finite dimensional module for UQLG, you restrict it, and possibly you twist it by some of this character lambda. So, so now M is any monomial in the YI8. Okay, so, well, using that, you can show that the botanic ring of the category C embeds into the botanic ring of the category O. So I'm almost able now to state our result. So it turns out that the category O now is too big in comparison with a cluster algebra. So we have to use what we call O plus, and that's not too bad. O plus would be the subcategory which is generated by the finite dimensional modules and by the positive prefundamental modules. You don't take the negative ones. You could also define a similar category O minus, which would work quite the same. So now, in order to be really precise, so we had this cluster algebra A, you remember, associated with a quantum matrix. Now we have to take into account all these weights, lambda, that occur in this category. So we are going to extend the cluster algebra by the group algebra of the weight that is of P, of G, sorry. And we call, on the other hand, O plus sub Z, the subcategory of O plus, where we add some restriction on the zeros and poles of these rational functions, which are the highest weight of our representation. In principle, they can be any complex numbers, but again, I want them to be essentially integral powers of Q. And now I can state our theorem that you remember we had this initial seed where the cluster variables were called Zi, and the idea is that now the interpretation of these ZIs are the classes of this positive prefundamental modules. So up to some twisting by some of the weights here, so that's why we are introducing this group algebra of the weight lattice here, but this is really a very mild question. We can ignore it for the moment. The idea is that we really can do this, and then we show that this gives an isomorphism from essentially the cluster algebra to this quadratic ring. So I have 5 minutes. I want to try to convince you that this is not trivial and what is the content of this theorem. So let's go back to our type A2 example. So now instead of having some abstract cluster variables attached to this initial seed, now we want to put here what was mentioned in the statement of the theorem, namely essentially the classes of the prefundamental positive representation. And here in gray, I have written precisely what are the little weights that we have to twist them with. This is minor. You could ignore these gray things in the first place. Okay, so you see we have positive prefundamental representation everywhere. Now we can start mutating. So let's mutate this vertex here. So we know how the quiver mutates. This is from the Levinsky quiver mutation. And we also have now a new cluster variable appearing here, which is called mu12 of this, which we had before. So let's do the calculation. So the calculation is given by forming the Levinsky rule, and you get this fraction here. Oh, but we're talking about Grothendieck ring. So what does it mean now to divide by the class of the simple modules? So this calculation apparently is now in the field of fraction of the Grothendieck ring. But fortunately, this is the meaning of our theorem, that this is going to simplify. And in fact, this boils down to the class of another simple module in this category O. Now with a more complicated highest loop weight, which is a product of a y and a psi, right? But already to prove just this little formula requires some work. It's not at all obvious. You have to work with these infinite dimensional representations, and it's not obvious at all. Now, remember we started with this mutation mu12, and when we did 2 mutations to get something which was finite dimensional. So if we do the same here, if we mutate now a vertex 2, 3, we get this formula. You remember we had a sum of 3 terms. And now the 3 terms in terms of the classes of the prefundamental representation, they are given like this. And here is the miracle that in the Grothendieck ring, or field of fractions of the Grothendieck ring, this is just equal to the class of this finite dimensional simple module. And the reason for that, which is also the sort of explanation of this change of variable, which I started with, is this result of Frenkel and Hernandez, which I find really amazing. So they proved before our paper that, okay, you start from a simple, or actually an object in the category of finite dimensional representation, what I call C, of UQLG. So you consider its Q character. This is a certain Laurent polynomial in the variables yia. Now you perform the following substitution. Each yia, you replace it by the following fraction. And you can see that this is almost the same formula that we had before. And then what they show is that if you do this in the Q character, and if you also replace the Q character of m by the class of m in the Grothendieck ring, and if you simplify denominators, what you get is a valid relation in the Grothendieck group or Grothendieck ring of the category O. Or you could say this is a valid relation in the fraction field. So this means that here, this is how we can show that these two things are equal. This is one instance of this proposition, of this theorem. So I'm almost done. I just want to say that we also conjecture now that, like in the previous types of conjecture, that all the cluster variables and actually all the cluster monomials should correspond to some simple modules. But this we are far from being able to prove it at the moment. Now it is category O+. And what we can prove is that this is 2 in type A1. It's not very impressive, but it's a start. And we can also prove that this is 2 for one-step mutations. So the calculation which I mentioned before, we can prove it in general for all types. And this again is not too impressive, but it turns out that this was enough for David and Frankel to prove a very important theorem in the theory of integrable models, namely that so-called Bethe-Amdahl's equation, which is a long-standing conjecture for this kind of integrable models, are satisfied for all the integrable models coming from representation of Q2H. So it turns out that this can be shown just by using this one-step mutation, which I find amazing. Okay, thank you.
Thank you very much. Are there any questions? Well, I see none. So we have a coffee break until 10:20. Let's thank the speaker again.